What do we want? Crystals. How do we want them? Defected.
Hey, how do you do? My name is Eric. I've teamed up with James and Brendan, and together we'll be talking to you guys about this magical thing called crystal defects. There are two specific kinds that we'll be talking about. We'll be talking about line defects and point defects, and there's even more subsets in these two categories. So we'll all get into this and we'll explain it in this video. But before we get started, be sure to hit like and subscribe. And without further ado, let's get into it. Hey there, I am out here in this beautiful Canadian weather. Of course, it is snowing in November. And I'm just going to be talking to you guys a little bit about point defects in crystals, and more particular, I'll be talking about the Frankel defect. It is a little bit different than the Scotty defect. We'll get into that later whenever we're out of the cold and snow here. But first, I just wanted to bring you over here. We have a chicken coop. If you can see past the snow, you'll notice I put some black and red dots representing cations as black and anions as the red dots. These are supposed to represent the ions in any molecule or anything of the sort, crystal. And if you notice right along, it's difficult to see with the snow, but right here there should be a cation. However, it is displaced, and this is what we call the Frankel defect. But what makes it special and different from the Scotty defect is that it's not simply removed from the lattice structure entirely. It is actually moved to an interstitial, I believe is how you pronounce it, interstitial position in between other cations and anions, which is where it shouldn't be, really. So that's really representing the Frankel defect. Now I'll just bring you guys inside so we can get out of this snow and I can talk to you more about these kind of structures and defects. Okay. So now that we are inside, the garage, I'd like to explain exactly what the Frankel defect actually is. When an ion, whether it be a cation or anion, is displaced from its lattice site, and it is moved to an interstitial site that is normally empty. Due to this, it actually experiences no change in its chemical properties. This is actually, in fact, the main type of defect found in silver chloride. This is due to the fact that the silver ions are softer, and so they're not quite as ionic as, say, for example, Na ions. And due to this, they can actually, it's a lot easier for them to remain in some sort of covalent equilibrium in between all the other ions in that interstitial site. An example of a crystal that does not exhibit the Frankel defect would be potassium bromide. Its ions are just too large, and it's very difficult for them to bond covalently due to their electronegativity. Also, its anions and cations are relatively the same size, so it's difficult for them to fit into those interstitial sites. And due to these factors, it's just impossible for potassium bromide to exhibit the Frankel defect.
So the defect that I'll be talking about is one of the point defects. It is actually the Schottky point defect. It has a stoichiometric vacancy of some of the sites within the crystal. However, the charge is still balanced, and it must have a neutral charge, as one of the cations or one of the anions, etc., will be vacant, leaving it with a neutral charge, but they will be missing. The example that I'll be using here is NaCl, using the spatula. As you can see here, we have a missing Na plus here and a missing Cl minus here. This is a Schottky defect. The way that this would look without the defect is like so. It's just a regular NaCl crystal here. They tend to associate because they carry an effective charge, and oppositely charged vacancies attract each other. At standard STP, 1 in 10 to the exponent 15 cation or anion sites are vacant. So this is a very rare defect. It's not common whatsoever. It is responsible for the optical and electrical properties of the crystal, in this case NaCl. It is the principal type found in alkali halides mostly. NaCl is a good example, or KCl is another good example.
The type of crystal defect that I'm going to be covering today are line defects, and the most common kind of line defect is a dislocation, which is a stoichiometric line defect. There are two types of dislocations that I'm going to be covering, and the first one is an edge dislocation. This is where in a plane of atoms there is an extra partial plane. So here, I'll show you an example that I made out of cue cards. So you can see that there's planes here, and then there's a partial plane here, which is the defect. And in a normal instance of this, without the defect, it would be like this notepad here, where it's all linear and parallel, and there's no partial planes inside of here. It's also important to note that point defects can lock dislocations into place, making the material harder. An example of this is steel being harder than iron. The second type of line defect that I'm going to be talking about is a screw dislocation, which requires a slip in a crystallographic plane. This is caused by shearing stress in a crystal lattice, and an example that I made here is this sort of cubic structure out of cue cards, but as you can see, this top part here is stressed over to one side like that compared to being a normal cube. And an example of this that would be defect free be this Rubik's Cube. As you can see, it's a perfect cube and there's no stress points in it to make it become misaligned at all. Something important to note about screw dislocations is that they occur most easily in closed pack CP planes. So CCP has 4 sets of CP planes, HCP has 1 set, and BCC has 0. So it occurs most easily in CCP. Thank you for listening to the presentation made by James Robinson, Eric Lorenz, and myself, Brendan Laframboise, on the differences between a few key crystal defects. I hope now that you know the difference between a Schottky defect, a Frankel defect, and line defects and their different kinds of dislocations. Thank you. Goodbye.